Okay, page 19 of the synchronization notes. So let's look at the same scenario as before. So basically, each task waits on first fork, then they wait on their second fork. So we need to draw that diagram again. So we got philosopher 0. I'm just going to draw roughly a star-shaped pattern of philosopher tasks. Okay, and then I'll put the forks in between them. Okay, so again, philosopher 0 acquires fork 0, philosopher 1 acquires fork 1, philosopher 2 acquires fork 2, philosopher 3 acquires fork 3. Remember, each one's getting ending their time slice right after they've acquired their first fork, and there's a context switch to another philosopher. So now philosopher 4, before we had them acquiring fork 4, this time they are trying to acquire fork 0 first. And so philosopher 4 is going to be waiting on fork 0. It hasn't acquired fork 0. So then what will happen is now philosopher 0, it may be waiting on fork 1, philosopher 1 may be waiting on fork 2, philosopher 3, when it goes to acquire fork 4, is going to be successful because fork 4 hasn't acquired it yet before it tried to wait on fork 0. So philosopher 3 is able to proceed, and when philosopher 3 is done, it's going to release forks 3 and forks 4. So then that would in turn allow philosopher 2 to finish, and so on, and eventually philosopher 4 would be able to acquire fork 0. So there is no deadlock, and there's also another concept of starvation. There's no starvation here. So there isn't any philosopher who is maybe just the odds are against them, and they end up repeatedly kind of losing a race to acquire mutex or something. They are going to block and wait until the mutex that they want is released, and it will be released, and then they will get it. So they are guaranteed to make progress.